yesterday.
I was here yesterday.
Not here.
It was school sponsored.
School sponsored.
It was okay.
I was being proud to be a pro.
All right.
What's that? Great year to be about now.
It was the most boring thing ever. I watched the simulation about 50 times.
Yeah. Yeah, going is kind of interesting, like going and doing it yourself, like for the first.
Like, it was kind of fun for like the first 2 or 3 times, but then after that.
Yeah, it gets old when you're just sitting there. Yeah.
Like, move the thingy to the right.
I was watching one girl do it, and she was really struggling.
I was so mad at Sugar because they made us move our cars. They could have told us to move them. So we had to park it all the way down.
You did what?
So unfair. All right. Okay. Continuity over an interval. So yesterday we were proving continuity at a point. Okay. So whenever we were looking at proving continuity, we were just looking at maybe like x equals 3. We were not talking about anywhere except for x equals 3. We were just talking about that single point. And there are going to be times where it's necessary for us to do that. Today we're going to talk about describing continuity over an interval. And so this first statement is going to sound like a dumb statement. But a function is continuous on an interval if the function is continuous at each point in the interval. Right? So it's not going to be possible for us to prove every single point in an interval because there are an infinite amount of points between, let's say, 1 to 2, right? There's an infinite amount of numbers between 1 and 2. So we can't prove every point, but we can disprove continuity on that interval because we can say, oh, here is this point where it's not continuous, therefore it cannot be continuous on this interval because it's between, if the function is not continuous at 1.5, then it cannot be continuous from 1 to 2. So that's what we'll be looking at. So there are some functions that are continuous for all points. Okay? Those will be polynomial functions. Polynomial functions are things, I'll give you an example out here to the side, like f of x equals x to the third minus 5x squared plus 2. Just variables raised to powers. Those are going to be continuous everywhere. And actually, we have a blank right here. Are continuous on all points on their domain. So polynomials are continuous everywhere. Their domain is going to be all real numbers. You're not going to have any holes, asymptotes, anything like that on polynomials. Rational functions, they are continuous everywhere on their domain, but a rational function, the word ratio is like fraction, a rational function can be something like 1 over x plus 2. Is that function going to be continuous everywhere? Not everywhere, just everywhere on its domain. So it's continuous everywhere except for the places where you have problems with the domain. So like the domain for this particular function, what number can your x not equal? -2. So the domain for rationals, your denominator cannot equal 0. So if they asked us about this function at -2, it is not continuous, but it is continuous everywhere else. So if they asked us about the interval from 2 to 7, that rational function would be continuous from 2 to 7. Okay? A power function is a lot like a polynomial function. It is just going to be like a x raised to any power here. It's a lot like a polynomial function, just a little bit. The power function can also include powers that super important. Power functions are going to be a domain of all real numbers. Exponential, that is going to be like f of x equals 3 to the x power. Domain for exponentials is all real numbers. You can plug any number into that. Logarithmic, the ones we're going to look at the most in this class are natural log, so it might be something like natural log of x plus 2. And those do have some restrictions on their domains. What are the restrictions on logarithmic functions? It cannot be negative or equal to 0. Okay, so whatever I'm just going to write inside. So whatever the inside of the log is has to be greater than 0. And, for this problem, x plus 2 would be the inside there. Whatever you're taking the log of. I wonder if there's a name for that. I don't know if there is, but there probably is. And then trig functions, I'm going to list these a little bit separately. If you have sine of x or cosine of x, both of those have a domain of all real numbers. The others have vertical asymptotes, and I'm not going to list all the places where they have those because they're repetitive, but the others are going to have vertical asymptotes. Maybe I was supposed to include roots. I either left off radicals or I meant to include it under power because maybe it fits under power. I can't remember. Radical, let's put that. This would be like f of x equals the square root of x plus 5 there. So the other option you could have is something like the cube root of x minus 7 or something like that. If you have an odd root, then your domain would be all real numbers. Because you can take the cube root of a negative number. You can take the fifth root of a negative number. So odd roots are going to be have a domain of all real numbers. But if we have even roots, what do we have for the domain for those? Like for this particular problem, can't have negatives. So now I do know the name for this. This right here, what's underneath the square root, is called the radicand. That just means the stuff on the inside of the square root. It has to be greater than or equal to 0. You can take the square root of 0. Square root of 0 is 0. So for logs, you cannot equal 0. For radicals, you can have a 0, but you cannot have negative numbers. So that stuff under there, that fancy word for that is the radicand. But all of these functions are continuous wherever they're defined. So like a square root function, if I've got square root of x plus 5, x has to be greater than or equal to negative 5. Because if you put in negative 6, you're going to get a negative in the square root. It's not going to graph. But it is continuous at all the points for which it is defined. So let's look at some of the problems that we're going to see. Oh, I was supposed to do all of that on the next slide. Well, it's already done. We squeezed it into a little tiny place when I was supposed to write it here. I should look ahead. I need to print myself a copy. Well, I got two sitting here. I have no good excuses for what I've done here. All right. So domains, we just went through everything, right? And wrote all that down, even though we were supposed to do it on this slide. Let's keep moving on. Show that f of x equals 1 over x minus 1 is continuous on the interval from negative 2 to infinity. Okay, so this is a rational function. So since this is a rational function, f of x is a rational function so it is continuous everywhere except, okay, where would this function not be continuous? 1, at x equals 1. So it's continuous everywhere except x equals 1. But they didn't ask us about everywhere. They asked us about this interval from 2 to infinity. So is f of x continuous from 2 to infinity? Yes, because 1 does not fall in that interval. So since 1 is not included in the interval 2 to infinity, f of x is continuous on that interval. It's starting to look like English class, isn't it? You ever had to write that much in your life on math problem?
I don't think I've ever had to write that much on English.
It's alarming. Okay, so basically for these, you're looking for the discontinuities, and if those discontinuities don't fall within the interval they're asking you about, then it would be continuous. If you do have a discontinuity, then we would say, no, it's not continuous on that interval. Okay, so I have this graph here. The graph is made up of a line segment and a point and part of a parabola. If g of x continuous on the interval from 4 to 8, why? Or why not, I should say. So if I look from 4 to 8, let's do a dotted line right here. So, like this, copy it. Oh. Got two dotted lines. 4. Oh, that's not what I meant to do. 4 to 8. Okay, so if I'm looking where x equals 4 to x equals 8, is this function going to be continuous on that interval? Yes. Okay, so yes, because the discontinuity is not included in the interval. Okay, so it would be fine from 4 to 8. All right, then the second one, though, asks us about negative 2 to 8. So I'm going to take this line right here, and I'm going to move it down to negative 2 if it'll let me. Why is it not letting me grab that? Negative 2. So we're looking here. Are we continuous from negative 2 to 8? We are not. We would say no, and then we can say at x equals 3. Now, what I would say for this, to be the most precise, what's the problem with this? Does the limit exist at that point? Yeah, limit exists. Does f of 3 exist? Yes. So the limit exists, f of 3 exists. Those are the first two things we got to prove for continuity. But what's the problem? They're not the same. So at x equals 3, the limit as x approaches 3 of f of x. I don't really have to say at x equals 3 since if you leave that out, it's fine. So limit of as x approaches 3 of f of x does not equal f of 3. Thus, I should be using g's here. You want your variables to match. The policy for AP is that, like if I did that on this problem, if it was a free response question, they'd give it to you because there's no other f of x. It would just be, they just made an error there in labeling, but they wouldn't know. However, if the problem also had f listed somewhere else in the problem, like in a part A somewhere there was a f of x, you would get no points because they would assume you were talking about f of x, even though you really weren't. So thus, g of x is not continuous on negative 2 to 8. All right, I should say, sorry, at x equals 3, and therefore not continuous. Oh, we learned this yesterday. Mathematicians try to avoid words as much as possible. We don't like doing this, writing all this out. So this symbol right here, these 3 dots, means therefore. And it is an acceptable mathematical symbol. So if you don't want to write out therefore, in my class, just put the 3 dots. I don't know that Miss Cox is going to accept the 3 dots if you put that in your essay, or Miss Soiree. Probably not, I would say. If one of y'all wants to throw that in and test them out, I support that, but I would not do it on a high stakes something that's going to be graded closely.
Mathematically correct, so mathematical things are like I don't, English is very important, but I have a t-shirt. I haven't worn it in a long time because it's a little bit too big because I bought the wrong size, but it says that English is important, but math is importanter.
Yeah.
I really like that.
Numbers have made a language. Letters have made languages, I guess. But they can't make numbers.
Yeah, well, numbers make like everything else.
Except Roman numerals, but that's a different.
Math is like a language to describe.
Yeah, but math is
The
more
world.
better because it builds stuff.
I agree. We should also tell Miss Soiree and the whole English department
Like
that math is more better.
Like, cause like, there's like in math, it's like there's only one like big language, and like it's universal.
It is
And there's
more
like
universal.
thousands of languages in English. English is one of thousands.
Yeah.
Math is one of one.
Yeah.
Maybe someone doesn't speak English.
Yeah.
But
It is,
they'll
if we have kids come from other countries, now, a lot of times we have kids come from, we have had several come lately from other countries where their education system is not as good as the U.S., and so maybe, and we've had kids that have not been to school since 6th grade, and so they come and they struggle in math because their math skills are very low. But what's his name? The Vietnamese boy. What's his name? No.
Bill?
I can't remember his name. Anyway, he's a sophomore now, I think, but he was a freshman last year that was from Vietnam, and he has like a little thing that translates for him, and he like came over knowing almost no English. He did well for Coach Wood in math because he had strong math skills.
Okay.
And so even though he couldn't read the problems very well, he could figure things out because the equations looked the same and he could still do it.
Said that she saw your lab like 2 years ago.
Yeah.
She's just having to relearn it.
Yeah.
Imagine
Yeah.
like someone teaching like, I don't know, just like German probably, and then like you have to like decipher what they're saying.
Oh, and Paloma,
Numbers.
yesterday, I need to tell you guys this about Paloma because I think I told you guys this maybe the other day, but she could not get the calculator to work, and I couldn't figure out why. It was like a very simple problem that she was just like multiplying something, and she was like trying to get Addie to help her, and she had typed something in, and so she had typed in it was 449 times like 280 is what she was typing into the calculator.
Oh, it's because in
And
Spanish the commas are
Yeah,
pages.
most Spanish-speaking countries do not use the comma. Like Mexico does not; they use the decimal like we do. But Argentina apparently does use the comma because some countries use the comma where we would use the decimal
Like
point,
4.29.
and then they use the decimal point where we would use the comma.
Yeah.
So, like, if we were writing 2,392.68, the comma is optional, so you don't have to put it there. And it's the same with them as well. They don't have to put it there. But they would write it like that. Yeah.
We're just trying to show that too.
Spoken like a true American. Yeah. So, anyway, she was using the comma as the decimal point
They do that
yesterday.
in Europe a lot.
So, yeah, lots of Europe does it. Apparently, Argentina does it. I think that I'm pretty sure Mexico does not. I want to say most of Central America is still decimal point, but apparently Argentina. I don't know about the rest of.
I would be rich in Argentina.
Would you?
I would. Theirs is like hard on like 4 times their dollar.
Yeah, their prices might be different too, but I know whenever I went to Mexico, like, it was like 11 pesos for $1, but yet things cost not more, but they cost more there too, so.
Oh yeah.
Yeah. But,
Wait, what?
It's like the Simpsons thing.
No, in Dubai, like things are really cheap. Like under off.
well, it's all, money's, I mean, if you want to really get deep, like, money's kind of not real. We have created money so that we can trade, Like, so we decided to use $1 and we put this amount of value on $1, and it's actually always changing because milk now costs more than it used to cost,
We have collectively
So-
decided as a society.
But other
that
countries
we
use
are
a different
equal.
system, so it's we don't have time for that deep philosophical question there, but yeah. Yeah.
Birds are controlled by the government.
They have
That's what I'm
also,
saying.
the internet has also been showing me videos of people doing girl math that really gets on my nerves.
I love girl math.
What's girl math?
Girl math.
I've never heard.
Where
of
girls-
I wouldn't know.
I relate to it so much.
Where girls justify ridiculous purchases.
They're not ridiculous though.
I saw Maddox send me this day where he's like, I think I use the cash
Have you
out of
seen
my
the
wallet
Walmart
because
thing?
my bank account doesn't go down, so I'm not.
Yeah. Yeah. Or
It's been like that.
my husband just bought a bicycle, and he sold an old bicycle, so it didn't count. Then, I told him, oh, well, you won't have to go to the gym. Well, he doesn't pay to go to the gym anyway. But now, you won't have to go to the gym, so that's like $80 a month. So you're saving $80 a month. So it's only going to take you 6 months, and this bicycle's going to be making you money after this point. So, anyway. Yeah. All right. Okay. Back to example 3. If you haven't looked up some examples of girl math, go check it out. It's not real math either. It's just a way to justify buying things that you otherwise maybe shouldn't. Yeah. Everybody spends their money on something, so if you're spending money you don't have, that's a problem. But what some people decide is valuable to them might not be to you, but that's all right. All right, so is f of g of x continuous on the interval from negative infinity to infinity? So to answer this question, if we can find one point of discontinuity, then we can answer this question. We can say no, because if there is any discontinuity, then it is not continuous. So whenever you're doing composite functions, you want to look at the inside first. Okay? So for this composite function, the stuff underneath the square root, what do we know about it?
It can't be 0.
It can't, can it be 0? Can we take the square root of 0? We can take the square root of 0. We can't do natural log of 0. So that's why we get those mixed up. But this x plus 2 has to be greater than or equal to 0, which means that x has to be greater than or equal to negative 2. And so on the domain of g of x, x must be greater than or equal to 2. So we can say that since the domain of g of x is x is greater than or equal to negative 2, f of g of x is not continuous on negative infinity to infinity. We actually don't even have to check the f of g of x here because we ran into the restriction right away.
So, if that very first one makes it not continuous, like the g of x,
Right.
you don't even have to do the second one.
Now let's pretend maybe it was continuous. If it was continuous, then we would want to do f of g of x. And we would have 1 over square root of x plus 2 minus 5. And we would need to see like what made that denominator 0, and we'd have another discontinuity there. But in this case, you're running into the discontinuity right away, so you wouldn't have to worry about it. Okay, describe the intervals on which the function is continuous. Okay, so this is asking where it is continuous, which is going to be everywhere that it's not discontinuous, right? So we need to find the discontinuities and then basically just remove that. This is a rational function that is defined everywhere, except for x equals 3. And at x equals 3, we have this value here. So what I really need to know, this is going to be a graph that has a hole in it, and I need to know if this point right here fills in that hole or not. And the way that I'm going to do that is I'm going to look at the limit of that top function. So if I do the limit as x approaches 3 of f of x, that would be the limit as x approaches 3 of, I'm going to go ahead and factor x plus 3, x minus 3 over x minus 3. And if I plug in, I get 3 plus 3 is 6. What is f of 3. It is 3. Okay, since f of 3 does not equal the limit as x approaches 3 of f of x, f is not continuous at x equals 3. But it's just a rational function, and we said rational functions are continuous everywhere except for their problems with their domain, right? So we could say f of x is continuous on the intervals negative infinity to 3 and 3 or 3 to infinity. So that lists everything except for 3. You could probably also write that just like x such that x is not equal 3 if you use different notation there. Or you could write it as x is less than 3 or x is greater than 3. Questions? All right, so your assignment, no wait, we got one more. I don't know what that blank slide is for. Okay, this example is huge. And they're asking us for what intervals is f of x continuous. So the first thing I want to do is I want to look at each piece and decide where they are continuous. So e to the x. Let's just think, we don't have to think about our domain or anything. Is e to the x continuous? It's continuous everywhere. So wherever it's defined, it's continuous. What about x to the third plus 2x? Continuous all real numbers. What about 5x over x minus 2? Okay, I can't have a 0 in the denominator. So x cannot equal 2. Is that on the interval it's defined for? Yes. So that's an exception on my domain. I need to keep that in mind. Okay. And I think this is going to be more of like a multiple choice question, so I'm not going to do the long explanation. What about cosine of 3x? Cosine is continuous. So cosine is going to be continuous everywhere. Tangent is not, but sine and cosine are continuous everywhere. Yeah, yeah. Tangent has those vertical asymptotes. And the reason it has it is because tangent is sine over cosine. So anytime cosine is 0, you're going to get a vertical asymptote there because you got a 0 on the bottom. So as far as just these go, we just have a discontinuity at 2, right? These should be continuous everywhere else, but we've got to check where the pieces line up, right? So if we do, I'm going to use limit notation just to be a good teacher here. If we do the limit as x approaches the left of f of x, we would get e to the negative 1, which is 1 over e. I doubt the other side's going to match that, but we'll just leave it. So limit as x approaches negative 1 from the right of f of x would be negative 1 to the third plus 2 times negative 1. And that is going to give us negative 1 minus 2. So negative 3. Do those two match? They do not. So we are going to have a discontinuity at negative 1. So we got 2. We got negative 1. We need to check at 0. Okay. If I do the limit as x approaches 0 from the left of f of x, from the left I would be using the second function, 0 cubed plus 2 times 0. That gives me 0. From the right of f of x, I would get 5 times 0 over 0 minus 2. So 0 over negative 2, which is also 0. So what about 0? It's fine. Okay. And then the last part, we got to check 4. I feel pretty sure 4 is not going to match up, but let's use our limit notation just to be a good example here. From the left, you would have 5 times 4 over 4 minus 2, so 20 over 2, which is 10. From the right, I would plug in the cosine of 3x, so cosine of 3 times 4, which is cosine of 12. Do we know that? That is not on the unit circle. Do we feel pretty confident it does not equal 10? Do we know it does not equal 10? How do we know it does not equal 10? Right, cosine is between 1 and negative 1. Right, unless you have a number on the outside, it's between 1 and negative 1. So I don't know what this is, but I know it's not 10. So x cannot equal 4 also. So this asks us to tell the intervals where this is continuous. So we would say continuous on, we would go from negative infinity to negative 1. Make sure you use parentheses, not brackets here, because we don't want to include that negative 1. Negative 1 to 2, and then 2 to 4, and 4 to infinity. Okay, questions? All right, homework is on AP Classroom again. Oh wait, wrong thing. So complete it on the AP Classroom. I'm pretty sure I didn't print that one, did I? Let's see if I put the PDF in case. I have not posted the PDF. I'm going to do that right now in case you run into issues. So if you run into issues with AP Classroom and it's not letting you do it, I will post the PDF every time. So do like Jeremy did last night and do it on paper if you need to. I'm going to do that right now so I don't forget it.